Hello, teachers. My name is Quoc, um, Hoang, and today I will present about last one have group six, and my name is Hoang. So let's get started with my presentation. Out of my presentation, I will split it in two parts. The first thing is explain definition, which contains some of like difficult theory or definition that we need to know before to practice. And the part two is practice. Just do one thing apply all the theory in the CPU sim to see the way how a program progress in the CPU sim. So let's get started. The first thing is instruction. An instruction is a command or operation that CPU need to perform. These instructions are represented in a specific format or contain information about what the CPU should do, such as arithmetic operation, data movement, or control flow changes. The next one is micro instruction. You can see here is the fast sequence, and in into that it have some micro instruction like yeah, PC and into MAR and so on. And then the definition of micro instruction is a low level instruction that specify detailed operations to be executed by the CPU. And these micro instructions are part of the microprogramming control unit and are responsible for controlling the internal operation of the CPU, such as reading, writing, or register to register, performing arithmetic operation, and handling data transfers. Mm, Program counter, which is the mm, a register that keeps track of the address of the next instruction to be fetched or executed by in the memory, and it helps the CPU know where to fetch to the next instruction. The next one is ACC, which is stand for accumulator. And an accumulator is a register in a CPU, which is central processing unit, used to temporarily store data and perform arithmetic and logical operation. And it's a fundamental component in many computer architectures and play a central role in arithmetic and data manipulation. The next one is MAR and MBR. The memory address register MAR is a CPU register that holds the memory address where data or instruction are to be read or from or written to in the computer's memory. And the next one is MDR. MDR is memory data register. The memory data register is a CPU register used to temporarily store data that has been read from memory or is about to be written to memory. So we just like uh, focus on mm, two things in this definition is MAR, which is stand for store temporary address, and MBR, which is MDR, which is which is used to store temporary data, and that's it. The next one is ER, which is instruction register. Uh, the instruction register is also a CPU register that holds the current instruction being executed, and is the instruction fetches from memory that is ready to be decoded and executed by the CPU. The next one is the decode. Decode is one of the part of the circle in in the process of computers. And the decode is the process interpreting the content of the instruction in the ER. During this step, the CPU determines what in operation the instruction specify and what data should act to. The decoding process set up the necessary control signal and operation for executing the instruction. One of the thing I is really important is now about the number system, which is in this presentation I will introduce you three of system number. The first one is decimal number, which is really like familiar with all of us. Like it's based on tens numbering system, which is the most commonly used numbering system in daily life, and the symbol representation is you digit from 0 to 9 to represent numerical values. Okay, the next one is binary number. Binary number is based two numbering system, which is 0 and 1, and two, and yeah, it's like just 2 0. The next one is hexadecimal number. Hexadecimal numbers are base 16 numbering system, and hexadecimal, which is also called hex, use character from 0 to 9 and A to F to represent numerical value. While 0 to 9 represent value from 0 to 9, and A to F represent value from 10 to 15. Mm. Next one is instruction format, and the default has in the like the machine demo, the CPU config would have default 16-bit length, which is 4-bit opcode and 12-bit address. Instruction format either structure in which a computer instruction is organized and represented in memory or computer files. It typically consists of two component, the opcode and the address or operands field. The number of bits allocated to each part of the instruction format can vary based on the specific computer architect. Yeah. And you can see here is some of opcode and which name in the third column, and the opcode value which is user by writes by hexadecimal system number, and which is stop we have opcode is 0, and load which is opcode we 1, star is opcode 2, and so on. Yeah, as you can see here, either opcode and address instruction format, which is write 4-bit of opcode and 12-bit of address. 4-bit of opcode is from 0 to 3, and address from 4 to 15. And it has some explain of internal CPU register, and you can see here is the partial list of opcodes is user a binary system number to use in this example, and which is 001. It means that load AC from memory, and 0010, which is store AC to memory, and 0101, it means that add to AC from memory. So we can like we will practice it in the last one with CPU sim, and I will demo all of things to you. Mm, the next one is the hardware and software approaches. Like in the picture A, which is programming in hardware, we can see that data and is input into sequence of arithmetic and logic function as will like release the results. And in the picture P, which is programming in software, from instruction code, instruction interpreter, followed by control signal, and the data will go through general purpose arithmetic and logic function as will release the results. And this is the two kind of view that we see. The first thing is in hardware, and the second thing in the software. And The next one is really important. It's a computer component from top level view. So we need to understand it, and we will like do the practice. Well, the basic function performed by a computer is execution of program, which consists of a set of instructions stored in memory. And the processor the act toward work by executing instructions specified in the program. This section provides an overview the key elements of program execution and is a symbolic form. Instruction process consists of two steps. The first one is processor reach or fetch instruction from memory one. Yeah, and mm, the next one is execute instruction, program executor instruction, and from program execution consists of repeating the process of instruction fetch and instruction execution. The instruction execution may involve several operations and depend on the nature of the instruction, and it will process required from single instruction is called an instruction circle. That's just some like the theory, and you can see that in the CPU it has some also register that I present in the previous slide, which is PC, which is MAR, MPR, ER, execution unit, IO, AR, and IOBR, and which is a system bus, and in the right hand is the main memory, and it below here is the IO module, and yeah, it has some like stand for and explaining here. The next one is basic instruction circle, and like I say before, when we run each instruction, um, when we run each instruction, it will like consist of like series of micro instruction, and in one instruction it have the circle of that, which is fetch circle and is execute circle from at the beginning of the instruction circle, like processor fetch an instruction from memory, and is a typical processor and a register called the program counter PC hold the address of instruction to be fetched next, and unless told otherwise. The processor always increase the PC after instruction fetch so that it will fetch the next instruction in sequence. The fetch instruction is loaded into a register in the processor known as the instruction register. The instruction contains bits that specify the action the processor is to take. It means that what I said before. Of course it have the it will the word is have the 16 bit, and it will 4 bit of code, and 12 bits of address, and in that when it's reach the data from main memory, and it will consist of the function, or it will like decode the value from it fetched from main memory, and it will follow by the micro instruction that's config in the CPU. It will do the particular action from the top level view. And this is the like the end of my presentation about the some theory and definition. So thank you for listening. And in the next video, I will present about how we can do all of these things into CPU sim 4. Um, let's get started with my practice with last one of CPU sim. So the first thing is I want to introduce about my computer that I use in here, which is the main the host CPU, which the host OS is the Linux. I use Linux Debian 12, and because CPU sim is have some error when I run it in the Linux, so I just like do the virtual or OS virtual machine, which is Windows 10, and just run the CPU sim 4. So when we download in here, we have download the Java setup, AU 391, and the CPU sim 4. So click in the CPU sim 4, and in here we will see that here is some more the uh, the bat file, which is the CPU sim 4 here, and all the thing is library. And in sample assignments, I will instruct you about some content, which is W1 slot Euro.8, which is the assembly program, and winbus1.cpu, which is the CPU config default, and it's the CPU sample that we run in all the all the thing in the CPU sim one of that 4. And in below here it have the one bat one, which is it either it is the all the config of the sample machine, which is Wombat one, and it have the like we can see that the first thing is register, and it is set up the PC, ACC, ER, MAR, MDR stated, and with PC, which is store address, it have 12 bits, and initial value is 0, ACC 16-bit, ER 16-bit, and MDR 16-bit, and MAR is 12 bits. Yeah, you can see that. In transfer RTOR, we will have some like micro instruction in here. For example, AR4 to 15 and to PC, which mean that we will read the bit from bit in ER register from instruction register from the bit 4th and to bit 15th, and it will shift into PC register. Uh, in the code here, I have the code ER, just some other basic thing. And the next one, we need to focus a machine instruction. In machine instruction, like I said before in the slide, in the theory video, we will focus on its stuff, and it have the upcode in hexadecimal is 0, load is 1, star is 2, rig is 3. And when we are doing the CPU sim, we need to know all of the things before we doing the CPU sim, because it will make us clearly when do with that. So let's get started. When we are in the CPU sim 4 down path file, which is here, it will running the application. So to introduce about the application, it have like four four part for four section. Like in the here is the first one is menu bar, which is have file, edit, modify, execution, and below here it have the in the register it's with name, width, and data. So PC, ACC, ER, MAR, MDR, and stator, and we have the data of all the register we need. We will choose this one to appear in here. For example, like binary or decimal, and we will use all the my practice is I use hexadecimal system number. So in the center of the application is the assembly editor, and we will load it from the W1 slot 0.8, which is the file that I identified before. Like it have some basic programming language, and it is a instruction, and the right one is the main memory, which is a thread. We can choose the type of system number that we need to display, like decimal, like hexadecimal, or bin. and we will choose that is hexadecimal. And in the data, we will decimal, hexadecimal, or binary. And I will choose hexa too. And in the section below is either input from which is control terminal that control that we input, or it will appear input or output um, that we enter from keyboard, or it will output um, from when running all these things. So the first thing we will uh, reopen machine that we open the CPU config in here, my machine here, and for example, I will do all of thing when I open machine, and I will choose one bus CPU one. Yeah, you can see that it's here, and it have the name of the CPU in here, and in the thing we will W uh, 1.0. I turn it off, and I will reopen it. Okay, I reopen it, and in this main memory. So before, and we will start to execute all this program, and we'll see the demo. We will choose the button, and we uh, select debug mode or control D. Yeah, in here it will show the like function in function bar, like set goal, status, instruction, step by instruction, step by micro instruction, and hit the fast sequence, which is series of micro instruction. So I will demo in the instruction first and micro instruction later. So we will before we execute it, we will load the example and load. Yeah, you can see that data is loaded from the CPU config, and it have like data in here. Let's get started. We will step by the instruction. So the first thing is we'll running in this line, and we'll read the end, and it save it in the ACC register. For example, I will enter this one, enter it, and you can see that in the assembly editor, it will jump in the it will move to the jump end function, jump end instruction, and jump to then if n is a less or less than 0, and in the main memory it will like move to the address and data in here. Address is 2, and you can see that because the PC in here is will pointer to 2, which is the address in the main memory. So as you can see that it is 002, and you can see that in the main memory. You can see that in here either 02, and it will have so we yeah, and in the we can see focus on the CPU SIM exchange. So we will like it will check if it will jump if n is the less than 0. So we will step instead next instruction. So you can see that the PC register is always like reload the if in the next instruction like before, and the ACC, which is store the data, and ER, which is B008, which is either previous instruction like B00A, and in the B here it will decode, which is beer. B is the opcode, and 008 is addressed to the address that CPU need to like execute, and MAR, which is the address of the I of the uh, um, of the previous uh, of the current of the previous uh, um, address and MDR with the data of that. For example, in the MAR is 002, and you can see that in the main memory is 02, and it will have data in here. Data is the 16-bit, and you can see that it will it's two row in here, B008, and in the MDR it's B00A, and you can see that it's some like difficult for us to to see, but in the micro instruction we can see that it's clearly. So we which by the in the ER in here we can see in you can see that in the machine instruction B uh here is B00A, and in here you can see that upcode is B, so its B is .n. .n, it means that it will do the micro instruction is if ACC is greater or equal than 0, it will skip, and if not, it will load from bit 4 to bit 15 in the main memory, and it will shape into PC register, and it will end it. So you can see that in here, is ER in here. So we will let's step in by instruction. It will move to store instruction, and the PC will focus, will move to the um, next instruction. And the ER, it will load the previous previous data like 0 5 0 1 0 in here, and MAR is 0 1 0. M is the address of that address of MER, because it is store is sum, and it will move to the thing. You can see that it will this is the address of the sum address uh, um, of variable. Like you can see it the I have a tooltip in here. It's the it is sum, and it's the location where sum is stored, and the MDR, which is the value of the address address 0 10 0 is the 0. Okay. Now we will step next instruction. Uh, you can see that MDR, which is updated, is 1, because I input 1 in here, and in hexadecimal 1 is will display by 1. So in the sum, in the memory, it will shift its 1, its value, and this the address of some variable is 10 in here. You can see in the main memory, and we'll see in the here. Yeah, it have the value is 0 1 0 0 1 is the value, and in the next loop in the assembly, I will jump to start and loop, and I will input like 3, and it will plot, and when I finish it will plot in the sum value, just like the normal just other programming language, but it's assembly is low level language. Okay, so as we will step by next instruction, and it will return to the start point, and it will do the rig instruction. So you can see that PCs will currently it will appear the next the next instruction, and in the memory is 00, and in the register data is 00, and in main memory is 00. So step by instruction, and we will input in here. For example, I input is 3, I enter it, and it will jump to next, and PC it appear here is 002, and it will do the address in the main memory. So ACC a 0, ACC is 003, which is the value that I input in either input of my from my keyboard, and which is store the previous data of the address memory is 3000, and MAR is in here is currently is 000. Okay, let's get started. As will next instruction, it will check and done. If it's not, it will move on to the next instruction and do the next instruction. That okay. Store the sum. Store the new sum, and you can see that after finish the store instruction, the value of store it will update it in the store store address in main memory. In here you can see that is a 004, which is uh in the previous loop we have the one in this variable. By here we input 1, and after we input 3, and the sum of 1 and 3 is 4, and it will display it in the hexadecimal is 4, and it's 004. So that's just the basic. Okay, and we will move to the next instruction. Right, and it will return to the Rex, and at this time I will input in the negative number. Okay, so um step instruction. Okay, in here I will is minus for example it's minus 2, and it will check, and you can see that it will do the instruction, and when I click next it will finish this, and it will check. Okay, because this value that I input is the minus 2, and is less than 0, so it will jump to done, and it will load the sum in here. Okay, step next instruction, and it will write is PC is 00C in here, and we will write the final sum and stop. Okay, and we can see the output in here is 4, which is the sum of 1 and 3, and when it see the minus 2, it will skip the program, and it will output the value. Okay, you can see that it will execution halted normally due to the system of the bit heartbeat. It will the heartbeat here. Okay, so that's the other like program mm, about instruction by doing the instruction. So let's get started with do all thing with micro instruction. We'll start over, and we will exit the debug mode, and we'll reset everything from 0, and here is 2. Execution, we will select debug mode, and we'll load the sample and load. Okay, data is updated. So let's get started with micro instruction, and here is the fact sequence, a series of micro instruction. We focus on in the lines here, and the series of micro instruction here also. So the first thing is there we can see that PC 00, which is right here, and okay, it will do the next instruction is it will save the MDR value, and from the main to the index is MAI trace. In here we can see that MAI is 00, so the value of MDR is 3000. Okay, let's check it. So that's all the same that I predict, because and this next one is it will save the value from MDR to ER register. Yeah, it will like save the value from MDR to ER register. The next one is will increase the PC register into 2 into 2 like plus 2 in the register like is a 0 0. So after this function the micro instruction, it will update it like 0 0 2. Like check it. Okay, all the thing is really the same. Okay, and it will decode the which is the decode the ER, and we can see that ER in here is the 0 0, and as well see that in here name, and it have the address of uh, the 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 word bit in here, and we can sublet it by decode and address or decode operand and operand. So we can see that all of the thing is a user in this config of CPU. So when we do all the program in the CPU sim, we can see it clearly. So step by micro instruction, and it input uh, an integer and it's saved into ACC register. Okay, and the reason why is the input, and we will back to next the previous micro. So you can see that in the decode ER in here, it will decode the ER register, and currently the ER register is 3000, and in the config of this okay, I will like uh do it smaller. uh, you can see that uh ER currently is 300, and we'll split it by decode and address. Decode in here is 3, address is 00, and you can see that the 3 in here in the machine instruction is a 3, and it means that Rick. So it means that when you see the decode of the in the micro instruction, it will decode a decode and decode 3, which means that input and address is 3 0 0 and 0. So I will start the micro instruction. So it will input in and ACC. Okay, I will input is 1. It's the same as the previous example. Enter, and it will end the micro instruction. So it will exit the decode instruction in here. So step by next micro instruction. Yeah, it will jump to the decode. It will check the it will like do it here. PC it next the MAR and main is the MDR and MDIER, and repeat the all thing is the also. So we just like do the by click here. Click wheel. MER is 002. M MDR is B0. B008, which is the PC will like it will we can display the next instruction. So in the all thing, if you do mm, the thing by we can see that 002 is the next instruction, and it capture address and value in here, and value is will save into MDR, and MDR will save the value into ER also, like the value should be 008 and will save into the ER also. You can see that is ER is updated, it's the same like MDR, and it will decode the increase the PC first. So the PC currently is 002. So when it's updated, it will 004. Yeah, all things be the same. So it will decode. We will back up one micro. Decode the ER. The ER in here is B008, and in this means that B is the opcode and 008 is the address. You can see that B. We will check the micro instruction B, which means that jump N, and it's also the same in the assembly program. So jump B and jump n, which is address is 00A and 0A in here. So it's we will do that by check that by step micro. Okay, as well if ACC the ACC is greater or equal than 0. Okay, yeah, because the input that I enter is 1, so that's greater than 0, so it just skip. So step micro instruction is the updated for, and the MAR which is updated in the 004. Yeah, and it will get the value from main memory of address 004 is 5010 and updated in the MDR. And next one is update the ER register in the same of MDR. Yeah, and increase PC into NIC. Yeah, it's 006. It means that the next instruction of the store in here, which is as we pointer to 06, 006 in the main memory, and it will decode the ER. ER in here is 5010, and we can see that in the instruction, which is 5 in the X and 010 is address of the instruction of the micro instruction. So we have micro, and it will reach the ER, which is from 4 to 15. 15 bit, which is will when it's difficult for us when we can see that in the hexadecimal, and when we'll click in the binary, you can see that it means that it will get the address of the ER address from big 4 to big 15, which is address ER. Before it here it's 000 00001 000, and it will shape to MAR. It will shape in here. So we can let's see the step micro. The next, it will copy all the thing and we'll paste in here. Oh, you can see that ER in here is 0 0 0 0 0 1 0 0, and it will copy 12 bit in here and you paste in here, and it will get the value from MAR trace into memory and we shape into MDR. So we just move to hexa to see it more clearly. 12, you can see that. Add the sum and it will get the sum address and sum value. And so it will ACC plus ADM, which is ACC, the value that I input, and ADR, which is the value of the sum, which is saved into main memory. And so it will plot ACC into MDR, and it will shape to MCC. Yeah, as will currently it's temporary save ACC, which is sum from the previous sum and the input that I entered from keyboard, and save it in ACC. And in the next instruction, it will store the sum into it will get the value of ACC and will restore in the MDR, which is extract of sum in the main memory. So let's move to next instruction. At the store instruction, and we'll have the micro instruction also. So PC will pointer to MAR, which is say the address of PC to MAR. PC is 006 and MAR is 010 010. So it will update. So MAR after I run it is 006. Okay. And get the value of any draft from the main memory and shape it into MDR. Okay. Because MAR is 006, and you can see main memory is 06, and it will save 0 to 0 1 0, and we shape in here. Copy the save the MDR into ER register, and ER in here is 0 to 0 1 0. It will decode the ER, and ER is copy the um, the address in ER register and save into MAR. See that with to bin. Can see that EI here is the same in here, and ACC to MDR, which mean that ACC either the ACC, which is the sum that we are plot from the keyboard. The number from keyboard is E1 and the period sum, which is euro, and it will save in the ACC. And now in the store instruction, it will say the ACC into the MDR, and MDR, which is the sum in the main memory. Set micro, and it will 001, and it will end. Okay, so you can see that it will do it by thinking clearly. So we will do it faster, and we jump to start. Stab it. Copy MDR and save into ER register. Increase uh, this area here. Copy a update the PC into 2 unit. Okay. So the next one is decode ER is 9000, and copy the trace of bit 4 and bit 15 to PC. Yeah, so just do all the thing. PC, yarn, update, update PC. So decode ER, input integer, and set it into ACC. So I will, because we will do all the thing like the periods, but for make it fast, we will like enter a negative number like -2, and we will see the how it works. Enter it. Okay, it will end. Okay, it will jump to the next instruction, and in this thing, you can see that save the PC register data to MAI, which is present here, and get the MDR value from MAI trace in main memory. So and copy the MDR and save it into ER register. Increase PC into 2 unit. Okay, and decode ER. ER is B00A. So it will check if ACC equal greater or equal than 0 or is less than 0. So the thing that the number that I enter in here is the -2. So it's less than 0, and it will skip it, and it will do the thing. So it will copy from bit 4 to bit 15 and set it into AC and N. So it will jump into load sum, step micro, and ER save into ER, increase PC into 2 unit, decode ER, and copy the ER register from bit 4 to bit 15 and save into MAR, and get the value of MDR from main memory of address MAR, and MAR to ACC. And so now it's the next is right. The PC to MAR and get the value MDR, get the value of ER, increasing PC, decode ER, and output ACC. So it's when I run this micro instruction, it will get us the output, give out the output. So the output is 1 because we input the -2, so we skip in the program in here, and we use 1 in the sum of the thing. Okay, and we will run the stop instruction equal set heartbeat. Okay, and okay, so that's all the thing that is the last one need to present up to all of us. So I thank you for watching my presentation and my practice.